Welcome to this video lecture. We're going to solve an example problem, and we're really going to teach about how you apply the heat equation to get a temperature profile. This problem states that a large wall is 10 centimeters thick and it's used to retain heat from a colder ambient. So here we have, think of this as being like inside a wall, here's a cross section of the wall, and here is outside. So the inner surface temperature of the wall is 25 degrees C, and the outer surface temperature of the wall is 5 degrees C. So there's a 20 degrees C difference between inside and outside. So you might be adding heat in here through like your furnace, and you're trying to keep the inside warm. So we're asked in part A, calculate the temperature profile for a wood wall, and then in B, calculate the temperature profile for a steel wall, and then finally calculate the heat flux for both the wood and the steel. The problem actually states that the wall is large in terms of width and height. So it's a tall wall and it's a wide wall, but it is not super thick. It's only 10 centimeters thick. Basically what that tells us is that outside we'd expect there to be some air circulation, inside we'd expect there to be some air circulation, so whatever's happening is that air is gonna mix things up pretty well, and we'd have a pretty even temperature distribution going down the width of the wall or the height of the wall. However, when we look at the thickness of the wall, we see this stark temperature difference from here to here, so we expect that the wall is going to change in temperature as you go in the x direction. Alright, so let's look at how we go about solving this problem. So stop and think, how would you start to solve this problem? And your first instinct might be an energy balance, and that is a good instinct, and an energy balance will definitely help us here. However, in the last lecture videos we talked about the heat equation, and if you remember, the heat equation is based on an energy balance. It is an energy balance. When we've solved energy balances previously, we've solved these kind of macro level energy balances, and we're assuming that our entire solid is all at a uniform temperature, and we're just trying to figure out what is that temperature. Well, now instead of just this simple algebraic energy balance, now we have this differential equation as our energy balance. And what we're going to get as we solve this differential equation is not a single temperature, but rather a temperature profile, or an equation that tells us how does temperature change in terms of space and time. We're going to assume this problem to be at steady state, even though the problem doesn't explicitly say that. It probably should say that. So our accumulation term we can consider to be just 0. We won't expect temperature to be changing with time. So we can nix that term. We're not told anything about generation within the wall itself. There's no generation in the wall, so we can nix the generation term. And then because of we're assuming uniform temperature in terms of the width and the height of the wall, we can actually get rid of our y and z dependency. So what we're left with is this one-dimensional form of the heat equation, d by dx of k times dt dx is equal to 0. If k is constant, remember k is the thermal conductivity of the wall. You can see something like wood has a low thermal conductivity, and something like steel has a much higher thermal conductivity. It means heat is going to penetrate that steel much easier than it does for wood. So these, in each case, are going to be just constant. So k is not a function of temperature or x, so we can actually pull k out of this derivative. Also, we are only dealing with change in temperature with respect to one other variable, which is x. So this is no longer a partial differential equation. It becomes an ordinary differential equation. And now it can look like this. Okay, so one other thing we can do, we have two quantities. We have k, and then we have the second derivative of temperature with respect to x. So when you take two finite numbers and multiply them, if their product is 0, that means that one of those two quantities has to be 0. K, we're going to assume, is non-zero. It's not a perfect insulator, and there is not anything that's a true perfect insulator. So K is non-zero. So that means the second derivative of temperature with respect to x is 0. So that tells us mathematically we can divide both sides by k, and we're left with this equation. So now we know that the second derivative of our temperature profile with respect to x is 0. What does that tell us? Well, intuitively, if you're good at calculus, that tells you if the second derivative is 0, you're looking at a straight line. So we're going to expect our solution to be a straight line. But let's go ahead and go through this process of integrating. So I want to point out this, even though it's now an ordinary differential equation, it's still second order, which means that we're going to need two boundary conditions in order to solve this for a specific solution. So we're going to need two boundary conditions. We're actually given those boundary conditions here. We know that there's a constant surface temperature on the left and a constant surface temperature on the right. So we will use those boundary conditions later. And for clarity, we're going to specify this as x equals 0, and the other side of the wall is x equal L, where L is our thickness. Okay, so let's go ahead and solve this guy. So the first thing to do, we could actually break this back up into this form, d by dx of dt dx. This is just saying the derivative of the derivative is equal to 0. We could multiply both sides through by dx. So we would get something that looks like this. So we've separated. Now we're going to integrate. So when we integrate, the integral of this derivative, the integral of the derivative of dt dx is just dt dx. Then the integral of 0 times dx is just 0 plus a constant of integration. So we get dt dx equals c. We're going to need another constant of integration, so I'm going to go ahead and call this c1. All right, so now we're going to integrate again. So we're going to separate first, multiply both sides through by dx, and then we will integrate. So the integral of dt is just t. The integral of c1, or the integral of dx, is going to be x. So we get t equals c1 times x, and then we're going to pick up another constant of integration here. So now this is our equation, and this does confirm that it is in fact just the equation of a straight line. So the first derivative is a constant, and the second derivative is 0 because the first derivative is just a constant. Okay, so that's our equation. That is what our temperature profile looks like for the wood wall, at least. However, if you notice, well, let's go through and apply boundary conditions first. Okay, so we get that our temperature as a function of x is equal to c1 times x plus c2. So how do we apply those boundary conditions? So our first boundary condition states that at x equals 0, we get t equals ts1. So we would go ahead and plug in 0 for x, and we would plug in ts1 for t. So we're just evaluating this equation at this specific x value, and we know that when we do that, we're going to get ts1. So that lets us produce this other equation. So we get ts1 is equal to c1 multiplied by 0 plus c2. So the end result, if you do some quick algebra in your head, you get that c2 is equal to ts1. Okay, so now let's look at our next boundary condition, which states that at x equals L, so here, T is equal to TS2. So now we're going to do the same thing, and we'll just plug in TS2 for temperature, and we'll plug in L for X. So we get TS2 is equal to C1 times L plus C2. But to make our lives a little bit easier, we know that C2 is already TS1. So let's stop talking about this C2 that we don't really know what it is and start talking about TS1, which is this measurable quantity. Okay, so now we are left with one equation and one unknown, so we can go ahead and solve for C1. So we end up getting that C1 is equal to TS2 minus TS1 divided by L. So now we know C1 and we know C2, so we can plug those guys in for our constants, and we get that our temperature as a function of x is equal to TS2 minus TS1 divided by L, and then to get the x dependency back in there, we still multiply C1 by x plus C2, which is TS1. Okay, so now we could actually, this is an equation, we know everything in this equation. We can go ahead and plug numbers in there, and we would get that for any x, we can just run this little equation. So we get TS2 is 5 degrees minus TS1, which is 20 degrees, so our temperature difference is minus 20. We would multiply that by x over L, and L is actually 0.1 meters. It was 10 centimeters if you remember. And then we would add our TS1, which is 25. So let's simplify this a little bit further. We get that our temperature as a function of x is just 25 minus 200 times x. So what we could do is we could put this in Excel or Python and plot this, but this is the plot of a straight line. So at x equals 0, we get that our temperature is 25. At x equals L, remember L is 0.1 times 200 would be 20, so 25 minus 20 would be 5. So we can see we've confirmed that we have the correct equation. It works out at both of these guys, and it's just the equation of a straight line. So if we could superimpose a plot of temperature over this diagram of our wall, we would see that in fact our temperature is just a straight line, and because we enforced those boundary conditions, we've forced our line to go through those 2 points where we know the temperature. Okay, let's take a closer look. We're asked to figure out the temperature profile for wood in part A and then for steel in part B. So the only difference between those two walls would be that they have a different thermal conductivity. However, if you look carefully at our temperature profile equation, you will see that if we look at this variable form of it, you'll see that thermal conductivity doesn't even show up in this equation. So our temperature profile under these particular circumstances is independent of the thermal conductivity. So both the wood wall and the steel wall would have the same thermal conductivity. They'd have the same temperature profile. They have different thermal conductivities. The wood wall and the steel wall have the same temperature profile, but different, even though they have different thermal conductivities. However, let's look at part C. So we've answered part A and part B. We know that temperature is just 25 minus 200 times x, where x has got to be measured in meters. Okay, so now let's calculate the heat flux for both the wood and the steel wall. So the heat flux, how do we do that? We know the temperature profile. How do we go and calculate the heat flux based on a known temperature profile? This is actually something we've been covering in Chapter 2 we use Fourier's law. So for Fourier's law tells us that to get the flux, that is just minus k times dt dx. So dt dx in both cases is minus 200, and that would be units of Kelvin per meter or degrees C per meter. Either way is good. Okay, so let's look at the wood wall. The heat flux is minus 0.17 watts per meter squared per Kelvin. And then we multiply that by our the gradient of our temperature, which is minus 200, and I'll switch to Kelvin here. Kelvin per meter. Oh, my apologies, I did the wrong units here. That's watts per meter per Kelvin. I was looking at my units and freaking out a little bit. Okay, minus 200 Kelvin per meter. So when we do that calculation, we end up with, notice that this becomes a positive number because we have two negatives in there. We get that the flux through our wood wall is 34 watts per meter squared. Notice that Kelvin cancels out and we get watts per meter squared. So for the wood wall, we are losing heat at a rate of 34 watts for every meter squared of our wall. So is that a lot or not a lot? Well, let's compare that to the steel wall. Oh, actually, before we move on, so notice that we get a positive number. So Q, our flux, is positive. It could be negative. That's totally physically possible. We could have a negative flux, but what does positive flux mean? If we go back to our coordinate system, positive flux means that the flow of heat, or the flux of heat, is in the direction of our coordinate system. So we just see that heat is going from left to right, the same direction as our coordinate system. Could that ever be reversed? Certainly, if our T2 got much hotter and it became summertime instead of wintertime, then our flow of heat, we'd expect it to go back the other way. We would see that our temperature driving force switches directions, and mathematically we should see that this reverses. So that could be represented by a simple change in our outside surface temperature. We'd see the direction of heat reverse, but the math, up to the point where we substituted in numbers for the temperatures, the math would be identical, and our final answer would just be, we'd end up getting a negative sign here. Okay, this might be a little bit too much information, but I want to help you develop a really good intuition for these problems. In addition to being able to do the math, I want you to understand why the signs are the way they are, why heat is flowing one way versus the other way. So let's look at steel, the steel wall. So it has a much higher thermal conductivity of 14.3. So if we apply Fourier's law here, we get minus 14.3 watts per meter Kelvin multiplied by the same temperature gradient, 200 Kelvin per meter. We end up with 2,860 watts per meter squared. So if you're trying to insulate your home or your building and you have these two choices available, wood or steel, which one are you going to choose? You can see that wood, because it has that much lower thermal conductivity, means you lose a lot less heat, whereas the steel, you're losing quite a bit of heat. And that's how you apply the heat equation and apply Fourier's law with really not knowing a ton of information, but using what we know and the heat equation, you can actually glean just a whole bunch of information about your particular system. So heat transfer is fun because it's intuitive and it makes sense. It's not too abstract, and you can extract really useful things. You go from this really fancy and maybe even scary looking math to some information that could just be really useful, like how much insulation do I need, or how big should my heater be, or which material should I use to build a building. Thank you.